Hello. Today I wanted to show you how to build digital divide by N counters using two different common ICs, the 74LS74 chip, which contains 2D flip-flops, and the 74LS00 chip, which contains 4 NAND gates. Here is the pinout diagram for the NAND gate IC, and then here's the pinout diagram for the D flip-flop IC. So what is a divide by N counter? It is a circuit designed in such a way where the output goes through one low to high cycle or period for every N low to high cycles the digital clock input goes through. So if it is a divide by 8 counter, the output will display 1 period every time the clock input displays 8 periods. I'll break this down into two categories. The first being the easiest dividers to build, which are the divide by 2, 4, 8, and 16 counters, which only require the D flip-flops, a DC power supply, and the digital clock input signal. The second category will be the offbeat dividers that do not fit into powers of 2, for example, divide by 3, 7, or 13, or in general, any number between 2 and 16 that is not 2, 4, 8, or 16. The amount of D flip-flops you have is N. If you cascade N D flip-flops together, you have a divide by 2 to the N counter at your output. If you cascade 3 together, you have a divide by 2 to the 3 counter, or simply a divide by 8 counter. I'll explain this now in LTspice, which is a free circuit simulation program. This is the divide by 2 counter, which is the easiest of them to build. It has a digital clock input signal, 0 for low, 5 for high, and the frequency is 1 kilohertz. At the preset and clear node, you have a DC voltage source of 5 volts connected to them. And then at your inverting node, you construct a feedback loop into your digital input. I'll run this really quick. And then your output is taken at the inverting node. We'll zoom in a little bit here. So for every 1 period of your output, you'll have 2 periods of your input clock. So here is your divide by 2. When you're going up to 4, you're making a 2 to the 2 counter. Okay, so your N is equal to 2, so you need to cascade 2 of them together. You do that by taking your divide by 2 counter and you take the non-inverting node and plug it into the clock input signal of your next significant bit over. And you still keep your DC power supply to the clear and the preset nodes, which is still at 5 volts. And again, your output is taken at the furthest to the right, or your most significant bit inverting pin. And your input is still your original clock signal. So for every 1 cycle or 1 period of your output, there will be 4 input periods that have gone through. That is your divide by 4. The divide by 8 works exactly the same way, and your divide by 16 works exactly the same way. Theoretically, this can go on until infinity, but at this point, I think you're catching my drift here. So these are your easiest ones to build. Now we'll get on to how to build the more offbeat ones. So when building offbeat dividers, you must first consider what kind of divider you're looking to build. If you want to build a divide by N counter that is not 2, 4, 8, or 16, and for example the number is 7, you have to round up to the next power of 2 to determine how many cascaded D flip-flops you will need. So you round 7 up to 8, which is the next closest power 2 up. The power of 2 is 3 here, so we need to cascade 3 D flip-flops together. Each flip-flop represents an integer number exactly like each bit in a binary number represents some power of 2. The same is true for any amount of cascaded flip-flops. in a circuit diagram, or in a real life circuit, the D flip-flop that has the actual digital clock input attached to it is your least significant bit. It'll represent 2 to the power of 0, which is 1. The next cascaded flip-flop over represents 2 to the 1, or 2, and so on and so forth, all the way up to the most significant bit at the end. So for example here, this is the least significant bit with the clock signal attached to it. This represents the number 1, this represents 2, 4, and then 8. And this is your most significant bit all the way at the end. To build one of these circuits, we first must disconnect the preset nodes from the DC power supply. We then must consider how many bits we need to use. It will be the bits that add up to the number for what kind of divider we are trying to build. I'll go through a few examples now. I'll start with a divide by 3 counter. So the next power of 2 up from 3 is 4. So this is the base that we need to start with here. And we are going to disconnect the preset node from the DC power supply. So now we need to decide which bits we need to use. In this case, we're going to need to use all of them. This represents 1, this represents 2. 1 plus 2 is 3. Okay? So that's how we create our divide by 3. We do it using NAND gates. So to grab 1, we take from the inverting node of the least significant bit, plug it into our NAND gate here. To get 2, we grab from our inverting output of our most significant bit and plug it into our NAND gate. We plug the output of our NAND gate into both preset nodes, and we run it. Our output will again be off the most significant bit. Okay, so here is our output. Here is 1 period, 1, 2, 3 clock cycles. So here is our divide by 3 circuit. I'll do another example here. I'll do a divide by 7. So like I was talking about earlier, the next power of 2 above 7 is 8. So here is our base model we need to take from. Again, we're going to disconnect the preset nodes from the DC power supply. So here's 1, 2, and 4. So 4 plus 2 is 6, plus 1 is 7. So here is where things get a little bit interesting, but not super complicated. Just for reference, the input nodes of a 2-input NAND gate, if you tie them together, the output of the logic gate forms a knot. Just FYI. All right. So 1 plus 2 is 3. Now to add it to 4, first we can plug 4 into one of the inputs of our farthest to the right NAND gate, and we feed the output of our first NAND gate into our makeshift NOT gate here. And then we feed that into the input of our last NAND gate. And then just like before, we're going to feed the output of the furthest to the right NAND gate into all of our preset nodes. And we can run it. Again, our output is taken at the inverting node of our most significant bit. And this should form our divide by 7 counter. So 1 period, 1, 2, 3, 4, 5, 6, 7 periods of our clock input signal. Okay, and it works like this to build any offbeat counter you want. If you need to use more than one NAND gate, so for example here we had to use, or excuse me, if you have to use more than two stages, here we had to use all three. To tie the two additions together, you need to do this. You need to tie together a NAND gate, and then from the output of one, you need to feed it into the input of the furthest to the right. I'll just go through one more example. I don't know if that is entirely clear what I just said. But for example, if you wanted to build a divide by 10 here, we would only have to use two of the stages because 8 plus 2 is 10. So here is 1, here is 2, here is 4, here is 8. So we would need to tie this inverting output to this inverting output with an AND gate, and then feed that to the preset nodes of all four. But we only have to use one NAND gate to do that, so it's extremely straightforward. All right, and our output is off our most significant bit again. And this should give us a divide by 10. You can pause it and count it if you want, but I am fairly certain it is a divide by 10. Now, if you wanted to make this into a divide by 13, for example, now you need to take off of more than just one stage. So I'll start this one from scratch. So we have 8 plus 4 is 12, plus 1 is 13. So we're going to need to take from 3 of these stages. So we're going to need to use that same trick we used before. Okay, so we will tie stage 1. We'll tie stage 1. Well, you know what? We'll call stage 0 with stage 2. Now we're going to need to tie it in with stage 8. So we have 4 plus 1 here, which is 5, plus 8 is 13. Sorry, this is a little bit messy. I'm just trying to do this on the fly. All right, so using that same trick we talked about before, here is a divide by 13. And again, you can pause and count this if you'd like, but there are going to be 13 cycles of our clock for every one cycle of our output. You can use these ideas to build whichever kind of divider you might need to build or design. Just please note, if you're going to build this on a breadboard in a lab, you need to read the data sheets for these ICs. You need to understand the amount of voltages and currents these ICs can withstand and the requirements for them to operate. You also need to understand how all the lab equipment works, and similarly to the ICs, you need to understand how to safely operate the equipment. In simulations, you can't break anything, you can't set anything on fire. In general, it is a really safe way to test and build circuits. This video is simply exploring the fundamentals behind building these types of circuits and designing them. If you have any questions or comments, please don't hesitate to leave a comment. Thank you for watching, and I hope you were able to learn something. Thank you.